Today we're going to talk about tries, which is a data structure for searching with string keys that is remarkably effective in enabling us to deal with huge amounts of data that we have to process nowadays. Just as motivation, when we left off talking about searching algorithms or symbol table implementations, here's where we were. The best algorithms that we examined were balanced red-black binary search trees and hash tables. And with respect to the basic search, insert, and delete operations, red-black BSTs were able to guarantee that we can get those done in logarithmic time actually pretty efficiently. And for hashing, we get them done in constant time under certain assumptions that we could have a uniform hash function. And also for hashing, we need to compute a hash code. For binary search trees, we use a compare to function. And another difference is binary search trees, we can support more operations than we can support with hashing. Ordered operations, for example, getting the rank of a key in the tree and other things. And those are terrific algorithms, and we looked at plenty of good applications of those algorithms. But still, there's the question, could we do better? And the answer is that yes, we can do better. As with string sorting, we can avoid examining the entire key, which is going to give us algorithms that can compete and even beat these classic algorithms. So to get started, we're going to articulate an API for symbol tables that's specialized for the case when the keys are strings. So simply we just add the modifier string to our standard symbol table API, and we can take a generic value, but the keys are strings. And then we take all the methods that we articulated before, and for key type instead of generic, we use string. And this is going to allow us to develop efficient algorithms that take advantage of properties of strings. Our goal is to get some algorithms that are even faster than hashing and maybe more flexible than BSTs, and we're going to be able to achieve both those goals. This again is the summary of the running times for when in the case that the keys are strings for red-black BSTs and for hashing. Let's take a look at those. So if L is the length of the string and N is the number of strings, and then also the radix R is going to be a factor later on, but it isn't for these two. Then for hashing, for every operation, we have to compute a hash function, which basically means looking at every character in the string. Actually, in Java, string hash functions are cached, so sometimes there's efficiencies because you only have to and they're immutable, so you only have to compute the hash function once. And then this is roughly the amount of space that takes into account the table and the string size. For red-black BSTs, the analysis is a bit more complicated. For a search hit, you have to look at the entire string, entire key to check that every character is the same. And then the comparisons, depending on the nature of the keys, for a typical case though, it's something like log squared n. We had log n comparisons, but usually you have to look at something like log n characters in the key in order to get down the tree. For a search miss, you might find out before you get to the end of the tree, and same for an insert. So the running times are something like this. And then here's some experimental evidence that that we can use to test out these analytic hypotheses. And we'll just look at two examples. One is the entire text of Melville's Moby Dick, which we've used before, and that's about 1 million characters and maybe 200,000 strings. And out of those 200,000 strings, about 32,000 are distinct. And then this is another file of actors from the Internet Movie Database. It's much bigger, maybe 2 orders of magnitude bigger, and it's got maybe about 1 million different words. So we'll want our algorithms to do better than, or at least as well as, red-black BSTs in hashing on these data sets. I think our test is to dedupe these data sets. So that's our challenge: efficient performance for string keys, and try to come up with algorithms that can compete with the best classic algorithms. Now, in order to do that, we're going to look at R-way tries. That's a particular data structure that was invented actually really quite a while ago. This data structure dates back to the 60s. And the first thing to know about it is that the name is based a little bit on a pun. It actually is the middle letters of the word retrieval, but we don't pronounce it tree because then we couldn't distinguish it from binary search trees, so we pronounce it try. And this is a confusing fact of life that we've been living with for many decades now with this data structure. And let's look at what a try is, and we'll look at some examples before we get to the code. So for now, we're going to think of a try as some nodes, a tree structure with nodes, where we store characters in the nodes, not keys. And the other thing is that each node has R children, where R is the radix, the number of possible characters. And there's the possibility of a child for each possible character. Now, in the standard implementation, this is going to involve null links. We have to have a placeholder for each possible character. So there's a lot of null links in tries, and we'll get back to that in a minute. But to get the concept, we'll use this graphical representation where we have characters in nodes and we don't show any null links. And the other thing is, remember, a symbol table is associating a key with a value. So this try is built for this set of key value pairs. And what we do is we store values in nodes that correspond to the last characters in keys. And we'll look, so that's what these numbers here are, and we'll look at a little more in detail on how this try is built in just a second. So that's the basic idea. We're going to have string keys, we're going to associate values, and we're going to use this this tree data structure, but we're not going to draw the implied null links for now. So for example, in this try, so the root represents all strings, and coming out of the root is one link for each possible letter. In particular, in this try, the middle link is the link to a subtry that contains all the keys that start with S. And we go further down, each time we go by a node, we pick off a letter, so that this link, for example, goes to the try for all keys that start with S, followed by H, followed by E, and so forth. So now, out of all the keys that start with SHE, actually one of them, the one that has just those letters and then ends, has a value associated with it. So in the node corresponding to the last letter, the E, we put the value 0. And so that's how the try is going to look. So just given that definition, then let's look at how to do search in a try. All we do is use the characters in the key to guide our search down the data structure. So let's say we're looking for the key shells. So we start at the root and we go down the S link since we started with an S. Now our second letter is H, so we look to see if there's a non-null link that corresponding to H, and in this case there is. Now our next letter is E, so we look for an E. Now no need to examine the value here because we haven't looked at all the letters in our key yet. So now we look for L, now we look for another L, and then finally we find the S, and when we find the S we look to see if there's a value there. In this case there is a value, and so that's what we return, the value associated with the last key character. So that's a typical search hit in a try. Another way is, so that node was down at the bottom, but if you were doing a search for SHE, you follow the same path, but now when you get to the E, that's the last character of that key, and so we just return that value associated with that node. That is, the search doesn't have to go all the way to the bottom. It might terminate at an intermediate node, and we just return the value associated with the node corresponding to the last character in the key. What about a search miss? Well, there's two cases for a search miss. One of them is we've followed down the tree, picking off the letters in the key one letter at a time as before. And then when we get to the end of the key, we take a look to see if there's a value. In this case, there's no value associated with the last key character. That means there's no key in the data structure that's been associated with a value, so we just return null. Or the other thing that can happen is we can reach a null link. So our key now is S, starts with S, and then H, and then E, and then L, and now our next letter is T, so we look to see if there's a non-null link coming from this node associated with T, and in this case there's no such link, so we return null. That's evidence that that string, there's no key associated with that string in our data structure. So that's a search miss. Now what about insertion? Well, insertion is also pretty simple. We follow two rules. One is, again, we go down links corresponding to each character in the key. If we come on a null link, we create a new node that's associated with the character that we're on. And just keep doing that until we get to the last character of the key, in which case we put the value. So if in this try we're supposed to associate the value 7 with sure, we follow our path from the root to S, because our first letter is S, and then H, because our next letter is H. And then O, we ran into a null link, so we have to put a node there with the character associated with the character O, so that later searches for this key will be able to find it by passing through that node. And now we move to the next letter, and there's no node again, and the next letter, there's still no node. When we get to the end, then that's the last character in the key, and we put our value 7. And now we've modified the data structure, adding the nodes that are necessary for a later search to go through character by character and find the value associated with that key. So that's insertion into a try. Just to cement all these ideas, let's do a demo of how that tree was constructed from scratch. We have a null try. We're going to start by putting associating the value 0 with the string SHE. We start at the root node, which a null try just has that one node. Create a new node for S, create a new node for H, create a new node for E, associate 0. So the key is the sequence of characters from the root to the value, and the value is in the node corresponding to the last character. This try represents a symbol table that contains just one string, SHE, and associated with 0. Every other string, if you search for any other string in this try, you'll either end at a node that doesn't have a value, or you'll end at a null link. All right, so now let's say we put in the key SELLS, and you can kind of tell where it's going. We made room for it in the try. So we go for S, and now the second letter E corresponds to a null link, so we create a new node. And similarly, we go through and create new nodes for each of the remaining characters in the key, and then associate the value 1 at the end. So now we have a try that has two keys in it, SHE and SELLS. Now our next is to insert SEA. So now we have S. We already have a node corresponding to E, and so now we just have to create one new node, the one corresponding to A, and put our value 2 there. And now we're going to put SHELLS in. So we already have the S, and we already have the H, and we already have the E. So now we have to add nodes for the last 3 letters in that string and associate the value 3 with it. Now we're going to put finally a key that doesn't start with S. So that means we create a new node corresponding to the first letter of that string and to the other letter too, and then associate the value 4. And here's another one that doesn't start with S, so we create new nodes corresponding to each one of its characters and associate the value 5 with the last one. And now here's SEA. So this is, remember, our symbol table API is associative, which means that if we get a new value for a key that's already in the table, we overwrite the old value with the new value. That's the way, the convention that we've chosen for symbol tables. So that is easily done with tries as well. Now here's one more key, SH, and now we have to add a new node because there's no node that's a child of H that corresponds to letter O, so we have to create new nodes O for O, R, and E and associate the value 7 with it. So that's a trie that has precisely 8 keys. If you look for any one of those 8 keys, you'll get the value. If you look for any other string, you'll either come to a node that has a null value or go out on a null link, and so the search would be unsuccessful. That's a demo of trie construction. So now that you have a basic idea of how what tries are and how they work, let's take a look at what's needed to implement them in Java. The key idea in the trie representation for an implementation in Java or any computer language is that instead of representing a node as a character in the node, what we do is we represent the links as an indexed array with one entry for each possible character. And the idea is that the characters are actually implicitly defined by link indices. So just for example, we have this small trie that we built over here. In this case, the root has only one node below it that's for all the keys that start with S. The way that's represented in the real representation, and this is for efficiency, and it's the way that tries get their efficiency, is we have one link corresponding to each possible letter, and the only one that is non-null is S. So the character S is defined implicitly by the fact that that link that that corresponds to S is not null. Over here, there's from E to A, there's 2 links coming out of E. And the only way that we represent A is by having the first link be not null. If the link corresponding to a letter is not null, that corresponds to having that letter in the node that it points to. So in this case, we have E connected to A and L, so we have the entries corresponding to A and L filled with non-null values. So you can see immediately the correspondence between this trie, the way we've been drawing it, and the Java representation of it, where each node contains 200 or R links, if there's R different letters, and letters are implicitly represented by non-null links. Values go in the node. So for example, in this trie SEA, which is easy to follow down through the trie, we're looking for an S, and S is the 20th letter in the alphabet or so. We index into the 20th position, and that takes us right to S. And then E is the 5th letter, we take the 5th link, and then A is the 1st letter, we take the 1st link. So we can use the character as index into the array of links to quickly travel down the tree. Then when we get to the last character, we can check the value at that node that's stored in the node. One slight complication in the implementation that we encountered before with hashing algorithms and other things, we're going to need arrays of nodes. That's what our links are. So we can't have any generics within node, even though we'd like to. So we have to declare the value to be of type object, and then we'll have to cast it back to whatever type it should be when we return it, and we'll see that in the code. other than that little complication, this is a quite straightforward representation of tries, and it leads to a very easy implementation. So the keys and the characters are not explicitly stored. They're there implicitly because of the links. And that's a very important point to think about when it comes to implementing and using tries. Given that representation, this code for implementing try symbol table in Java almost writes itself. It's a symbol table implementation, and this slide has the implementation of put using the same recursive scheme that we've used many other times in building trees. What are the instance variables? We declare R to be 256. As usual in our string implementations, we're working with extended ASCII. And then we have one instance variable that matters, and that is the root of the try. So tries begin with, all tries start with a null node. So first thing we do is create a new node and put a reference to that node in root. So our empty try consists of a node that's got remember when you create a new node, we build an array of R links to nodes. And at the beginning, those will all be empty links or all null links. So the root points to a node that has 256 null links. Now, to put or to associate a key with a value in a try, we use this instance method that calls a recursive method, again, the same way that we've done for other tree construction schemes before. So it takes, the recursive method takes a node as argument and returns a node. So it takes a reference to a try and returns a reference to the try that it constructs after associating the key with a value. Just to get started, suppose that our first key has just one character. So in that case, we would call the recursive put for the root with our one character, so our one character key, and call the recursive routine. Now our node is not null, it's the root node, and our key is length 1, and we call it starting at 0. So the first thing that we do is pick out the dth character of our key, so the 0th character, which is our one character, and that gives us an index, whatever letter it might happen to be. Say it's B, then C would be 2, that sort of thing. And then all we do is recursively follow that link, insert associate our key value in the try pointed to by that link, and then take the link that we get and put it back into that link out of the root node. So the next call, there's nothing in the root.next, it's null, so the next call we get null, so we create a new node. And in that new node, at this point, we've called with d plus 1 moving to the next character. So now we have d equals 1, which is equal to our key.length. So we associate the value in that node with our node and we return it. So that return, one level up, will set the link of the new node in the appropriate entry corresponding to the root. Once you've learned our normal recursive way of structuring, building tree structures, this code is very natural. For a longer key, again, thinking recursively, we find if we're supposed to insert the key, associate the key with a value, and we're working on the dth character, we pick out the character at the dth position. We use that to index into the link array, the current node, and then that's the link that we set when we do a put of the new node. So when we start with a longer string in a perfectly empty tree, we create new nodes all the way down and then put their links to their parents all the way up in this recursive structure. and it's a very simple and natural recursive code. So that's the put. That takes a little study, but not so much once you're used to our standard recursive way of producing tree structures. And get is even simpler. So contains and get. So our standard convention is to return null if we have a key that's not there, and that's contains. And the get function is again a recursive procedure that will return a reference to the node, and if that's null, we return null. Otherwise, we can get the value out of the node returned by the recursive procedure. And then remember, we had to make our value in nodes of type object, so we have to cast that back to the type value. And the recursive get is very simple to find the node that contains the value associated with a given key, and we're working on the dth character, and we're currently on node X. We just return null if X happens to be null. That means it's not there. If we're at the last character in the key, we return our current node. Otherwise, we get that dth character and we use that to index into the next array of the current node and recursively call the get routine for that node, moving one down the tree and incrementing our key pointer by one. Extremely simple recursive code to do the try implementation. So what about the performance? Well, in a search hit, we simply go down the try, examining all L characters, just using each one to index into a next array at some node, and then go down to the end to see if there's a value there. Search miss, we might have to go all the way down to the last character, but we could also just have a mismatch on the first character and find a null link right away. And actually, typically in a try, in typical applications, we only examine a few characters. So right away, you can see by thinking about a search miss, that try algorithms can be sublinear. We can find out that a key is not in the tree by only examining a few characters. If we don't have any strings in our try that begin with the same few characters as our search key, then it's not there. That's a typical case. Now, the downside of try performance in lots of applications is the amount of space used. There is the problem that every node's got R links in it, and particularly down at the bottom, the leaf nodes that correspond to the last characters in keys, no prefix in the key in the try, there's going to be null links. Now, it is possible in a huge try with lots of strings that are short, sharing common prefixes, to actually use much less space than this. But the R null links at each leaf is a real problem in some applications, and we're going to take a look at how to deal with that. So the bottom line is, for symbol tables with relatively small numbers of string keys where the amount of space used by the null links of leaves is not a problem, then we get a very fast search hit and even faster search miss. But we burn up some space. That's the bottom line about try performance. And just a typical application, maybe you get a job interview question about what data structure do you use for spell checking. And this is just an example to show how effective tries can be for such an application where all the words are 3 letters. And the solution is build a 26-way try. So the spell checking usually there'll be pre-processing to strip out everything but the lowercase letters that make up the word. So you can build a 26-way trie that will immediately tell you whether you have a misspelled word or not. Another interesting thing about tries is that deletion is very easy. What do we do to delete a key value pair? Well, you find the node corresponding to key and set the value there corresponding to null. So that's easily done. So we want to delete shells, we cross out the value there. And now there's two cases. One case is this one where that node, now we set its value to null and it's got all null links. There's no reason for its existence. So it wouldn't have been created except for the fact that we inserted shells. So if the node's got all links, you just remove it. And then just delete it, and then when you go back up the tree, which you do because you got down there, every node that you touch, you check if it's got a null value and all null links, just delete it. And you keep going until you find one that has either a value or a non-null link, and then that's when you can stop deleting nodes. So it's pretty easy to delete a key value pair in an R-way trie, and that's unusual for other search structures that we saw. The deletion was a significant challenge to implement often. So our challenge is to find a way to use less memory, particularly because nowadays many strings are built with Unicode, and the number of null links in a trie would be truly huge. Again, we talked about this with radix sorting, that a lot of programs broke when the switch went from ASCII to Unicode. And any program that used this representation for tries certainly broke. So that's an introduction to tries with R-way tries.